Today we're going to learn about centripetal force. We're going old school today because my pen isn't working and not syncing with my laptop. So me and Boo, who's right here, are going to talk about the lesson via video. So we're going to start with a bit of a refresher, this one on uniform circular motion. We've talked about this before. Uniform circular motion is motion where we have an object that's traveling in a circular path with a constant speed. So for example, if we have this object here, a ball swinging around on a string in a perfect circle, the centripetal acceleration will be directed inward. The velocity is always going to be tangential to the motion, and the magnitude of that velocity will be constant. So, bullet points here, uniform circular motion means the rotation of the object is constant, the instantaneous velocity is tangential to the circular path, the magnitude of that velocity is constant, and the acceleration is also constant and always directed radially into the center of the circle. We've also learned before that the acceleration causing something to move in a perfect circle, called the centripetal acceleration, is equal to v squared over r, where v is the magnitude of the velocity. Now, to get from centripetal acceleration to centripetal force, we just add a little bit of Newton's law, Newton's second law, onto what we already know. So if Newton's second law tells us that F net equals ma, the only difference in this case is the acceleration is the centripetal acceleration, causing something to move in a circle. So in order for there to be a net acceleration towards the center of the circle, so that the object travels in uniform circular motion, F net has to also be directed towards the center of the circle. So now we call it centripetal force. So if the object is moving in a perfect circle, such that the acceleration is the centripetal acceleration, then the net force is just called the centripetal force, and we'll use a subscript C, Fc. So F equals ma, acceleration is v squared over r, so the centripetal force is mv squared over r. So not too much new so far. Next up, here's a little diagram. We've got a ball traveling in a perfect circle undergoing uniform circular motion. In this case, we're going to draw a quick little snapshot of what's going on. In this case, here's our ball undergoing uniform circular motion. At this instant here, the only force, we'll assume this is a horizontal circle, by the way, the only force acting on the ball is tension, which means if F net equals ma, then Fc equals the tension, which is just equal to mv squared over r. So there's always some actual force which is causing the centripetal acceleration. Here's some more examples to think about. If we have a satellite, and the satellite is going around, here's the Earth, going around the Earth, undergoing uniform circular motion, there's our satellite, what's the force that's causing the uniform circular motion? That force would be gravity. What's the force acting on a car that's driving in a circle on a horizontal surface? Wow. Horizontal circle on a surface. That would actually be friction. If we pretend we're looking at the back of a car, here are the wheels from the back, and the car is accelerating in this direction towards the center of a circle, the only force exerted on the car, preventing it from slipping outward as it goes in a circle, is actually static friction. Finally, if we have a roller coaster doing a loop-de-loop, the only thing keeping the acceleration of that car directed towards the center of the circle is some combination of normal force from the track pushing on the car and gravity. So as you can see, there are numerous actual forces that can cause centripetal force, resulting in an object undergoing uniform circular motion. Okay, on to some examples. In this first example, example 1, we've got a 75-gram ball. It's being spun, undergoing uniform circular motion. by a child. The ball is attached to a 50 centimeter string and tracks out a horizontal circle with a radius of 40 centimeters. So here's our situation. Yes, it requires a little bit of geometry to figure some things out. And in fact, the first thing we need to figure out is, what is this angle theta? We have a nice little triangle though to work with. This is 40 centimeters. That's the radius of the circle that the path the ball is tracing out. And we know that the string is 50 centimeters. So if we use a little bit of trigonometry, let's say here's the hypotenuse of our right angled triangle, here's the opposite side, here's the adjacent side, we can say sine theta is opposite over a hypotenuse, which in this case is 40 centimeters over 50 centimeters. Therefore, theta ends up coming out to 53.1 degrees. We ran that to 3 significant figures. That was easy for part A. For part B, we have to draw a free body diagram for the ball. Now there's a couple ways we can think about that, and I'm going to draw both of them. However, we don't need both of them to do our analysis. We could think about the ball side on. So let's draw that for a second. If we're thinking about the ball from the side on, we're looking at it from the front. So we have an up and down direction, and we have a direction that indicates the center of the circle. So let's say here's our ball from the side on. The ball is experiencing a tension force in this direction, and we've already actually figured out this angle theta. That angle was 53.1 degrees. And the ball's also experiencing a downward force due to gravity. However, gravity is not contributing to the uniform circular motion. In this example, t can be broken up into components. This would be t in our x direction, which would be t sine theta. This upward component of tension would be tension in our y direction, which is going to be t cos theta. In this case, we have an upward direction, which we can call positive. We also have a direction, which I'm going to label center of circle. You don't have to label it this way, but I often find it's easy to label it this way so that I get my bearings when I'm looking at a certain free body diagram. We can also think about drawing this from a bird's eye view. From a bird's eye view, we actually don't see, and I say that in quotations even though you can't see me, we don't see the gravity vector if I'm drawing it from a bird's eye view, because gravity would be acting straight into the page. So from a bird's eye view, there'd only be one vector that I would be able to draw, and that would be a vector equal to t sine theta, acting towards the center of the circle, just like in this drawing. So these are both drawings of the same thing. I'm just looking at different forces because I'm looking at it from a different perspective. Okay, C. We need to find the tension in the string. So let's use the free body diagram for the side view, since it gives us a lot more information and it's easier to visualize that way. So for the side view, in our x direction, we can still say F net x equals m times ax. Except in this case, F net x, the only component acting in the x direction, which is towards the center of our circle, is t sine theta. And the acceleration is our centripetal acceleration, so mac. T sine theta equals mv squared over r, since acceleration is just v squared over r. Now we need a little bit more information in order to solve this problem. So let's look in the y direction. And in the y direction, we also know F net y equals may. But in the y direction, there's zero acceleration. It's staying in the same plane in the y direction. In the y direction, I have this upward component of tension, so t cosine theta in the positive direction, and I've got this negative force of gravity minus Fg equals 0. So that's telling me t cos theta equals mg. Plugging in a few numbers here. Actually, this is solving part C because it was asking for the tension. So plugging in some numbers, I've got 0.0750 kilograms. Don't forget, 0.0750 kilograms is 75 grams, times 9.81 meters per second squared, divided by cosine of the angle we've already determined, 1301. This should come out to 1.22625 newtons to 3 significant figures. That's actually part C. I should have labeled it this way. So part C, therefore, the tension is 1.23 newtons. The next part is, how fast is the ball traveling as it swings? We can use this equation to solve for that, so I really should have called this part D. Let's just sub in. We know the tension, now we just have to solve for V, the velocity. V squared is equal to RT sine theta over m. Plugging in some numbers, and I'm not forgetting to take the square root. That's something that's very easy to forget to do when you're dealing with uniform circular motion and these equations. V is equal to 2.2874 meters per second. Therefore, the ball's speed is 2.29 meters per second. No direction needed, although we know it's tangential. Part E, how many revolutions does the ball complete every second? Revolutions per second. Revolutions per second is frequency. So we're actually asked for the frequency. There was a formula that you were given way back in the kinematics unit when we did uniform circular motion that related centripetal acceleration to frequency. And it was this one. Centripetal acceleration equals 4 pi squared r f squared. So rearranging this, AC is v squared over r equals 4 pi squared r f squared. Rearranging this, plugging in some numbers, we're going to get the frequency is 0.9101 hertz. So that's 0.910 revolutions every single second. So that is example number 1. We're drawing the free body diagram, except the difference this time is our net force is the centripetal acceleration. Here's another example. This time we're bringing in some cars. Get ready, we're going to bring in a lot of cars going in circles. Example number 2. A 1,500 kilogram car is traveling at 24 meters per second through a horizontal circular turn with a 100 meter radius. So we need to figure out things like how large is the centripetal force provided by the frictional force required to keep the car moving in its circular path? What is the corresponding minimal coefficient of friction between the tire and the road surface? Is it static or kinetic? And C, how would this coefficient of friction be changed if a 3,000 kilogram pickup truck were traveling through the same curve? So here's what I want you to imagine. We have this truck. Is it a truck? No, it's a car. It's a car. We have this car. The car is traveling in a circle. Here's our car. Here's the velocity of the car at this instant. Imagine the car, you have to kind of imagine the car is traveling on a slippery surface. Now, if there weren't friction and the car were traveling in this direction, would it be able to travel in this continuous circle? No, it would slide off. However, there is some friction acting on the car's tires, and that's allowing the car to make this turn and continually travel in a circle. So the force that is causing this car to travel in uniform circular motion, the force that is providing the centripetal force, is just friction. So the first thing we can do is we can draw a couple of free body diagrams, and just to help you out, this is just a sketch, not a free body diagram. Just to help you out, we're going to draw the side view and the bird's eye view. just to get in the hang of visualizing this situation and how friction is acting on this car. So here's the side view. We've got our car, here are the little back tires. We've got a normal force acting on the car as usual. We've got a force of gravity acting on the car as usual. But the thing that's preventing the car from slipping, the thing that's actually keeping the car traveling in a circle, is this force of friction. In this case, it is static friction. So going back to our question here, this is static friction because the car is not slipping radially. The car's tires are in constant contact with the surface. So we're not dealing with kinetic friction. We would only be dealing with kinetic friction if we were dealing with a situation where a car was skidding on the road. That's not the case. The wheels are in constant contact with the road. So this is static friction. Finally, bird's eye view. In this bird's eye view, we don't draw Fn, we don't draw Fg because that's literally straight into the page and straight out of the page. The only force we can see from a bird's eye view is this static frictional force. So in terms of our directions, in this diagram, we've got up and we've got this direction, which I'm going to label as center of circle. In this free body diagram, we just have center of circle, only interesting direction. So we have an idea of what's going on in terms of free body diagrams. Now we can go ahead and do a calculation. So the first thing we're going to do is write down Newton's second law. Actually, we can even skip that step right now. Since we're only asked centripetal force, we can actually calculate that right off the bat since we're just asked for a number. Centripetal force is always going to be mv squared over r, and actually we know all of those numbers. So we know for part A, how large is a centripetal force? It's just 1,500 kilograms times 24 meters per second squared, don't forget to square it, over 100 meters. This should come out to 8,640 newtons to 3 significant figures. Oh, hi Boo. Part B, go away. Part B is, what is the corresponding minimal coefficient of friction between the road and the car's tires to allow this car to travel in a circular motion? Now we can apply Newton's second law. We know F net x equals ma x. In this case, the x direction we chose is towards the center of our circle. In the x direction, the only force is static friction. And our acceleration in the x direction is the centripetal acceleration. So we've got mu s Fn equals m v squared over r. Now in the y direction, F net y equals ma_y. In the y direction, there's no acceleration. So we've got Fn subtract Fg equals 0. Therefore, Fn equals mg. Now we can do a little bit of substitution. Mu s mg equals mv squared over r. We take a look at our equation and we see that we can immediately make a little bit of a cancellation. There's an m on both sides. So we can get rid of m. Keep an eye on this step because it's going to come back in part C. So now we want to know, what is the minimum static coefficient of friction that would allow the car to travel in a circle? And we're actually finding that right now. We're finding what is the minimum static coefficient that would allow this car to be undergoing uniform circular motion. Mu s equals v squared over r times g. Putting in some numbers, we should get 0.58716 to 3 significant figures. Therefore, any surface with mu s less than 0.587 would cause the car to not travel. This is a very random way of writing this, but whatever. In uniform circular motion. I wrote that kind of a roundabout way. Anyway, we need that minimum static coefficient of friction in order for this car to travel in a perfect circle. Finally, C. How would the coefficient of friction change if suddenly the car were twice as massive? Well, we would do the same analysis. We would have exactly the same free body diagram. We would, of course, require a different centripetal force if the mass of the car were doubled. But let's look down here at our analysis. This analysis would apply no matter what the mass is. And as we can see here, mu s does not depend on mass because mass canceled out. So part C, mu s would be the same if the mass was doubled. Therefore, mass doesn't matter. So that is the end of example number 2.